Hello, everybody. This is an information video about the homework assignment that you're about to be given. Basically, I have combined homework 3 and homework 4 into one homework because everybody is busy. We have too much to work on these days. So basically, I've combined homework 3 and homework 4, and it will be an individual assignment. So we will not form any groups, and what you have to submit, I will come to that in a moment. So basically, homework 3 is a homework that has a simple model here. We have a mass, a spring, and a damping element, a damper. And we apply force as shown in this figure here. And this is the movement. So the physical parameters are given as m, k, and this is b. Unfortunately, it's missing its parameter here, but since this is only left alone, you can assume that this is b, because you have to know physical modeling from previous lectures. This is the damper element, and its coefficient is b. Now, you are given these coefficients, and here we have the mass as a calculation. You will use your student ID, the last 2 digits of your student ID, and you will plug in the sum here, and you will multiply it with 10. That will give you the mass that you are going to use in your homework. And then we have k and b, they are fixed to 1. And it is also known that there is an I/O delay of 1 second, which means that we have a delay from input to output. You will see in a minute why we need to use this. So the first question here is as follows. You have to calculate the transfer function between x dot and the control input u, which is equal to ft. So basically this is the control signal. This is the change in position, and if you take the derivative of it, it will be velocity versus the control input. So we are trying to control the velocity of the system. That's what the plan says. So, and there is also a delay between the velocity and the control input of 1 second. So first of all, you have to use this model here and the physical relations, and you have to acquire the transfer function. The second question is to design a controller. You can choose any controller from this family here. You can choose the PI, the PID, or the PIPD. It's up to you. And you're asked to use the Smith predictor. So, and our requirements are given as follows. You have overshoot equals 0. You know what this means, but you're not given a settling time, rise time value, which means that you have to choose it so that the overshoot will become 0, or at least as close as possible to 0. So there is no settling time, which means that you have a free parameter here. My suggestion is for you to start with the PI controller. If that's enough, you can stop there. If not, you can switch to the PID structure. And since you've designed the PID structure, maybe you may want to check out the PIPD controller, because there's a direct relation between the PID and PIPD structure. So one of them should give a good relation here. I left you free. The only thing is that you should try to minimize the overshoot of the closed loop as much as possible. And since this is a Smith predictor, you have to check out that video maybe, and you have to design it. And then the next task or question is here as follows. You have to design a controller of your choice again. But this time, instead of the Smith predictor, you will use the first order Putty approximation. The next question is about the second order Putty approximation. So basically, these 3 questions are used to design 3 different controllers for the same system. And let me remind you that you should, especially for the putty approximations, you should use the original system for your simulations, not the putty approximations. If you watch that video, you will see, or you will get what I mean. So then you're asked to use the body plot to find the stability interval of this transfer function, by the way. So basically we have a plant here that corresponds to this, which is modeled using these dynamic equations here. And we use it to design a controller, another controller, and a third controller. We designed 3 controllers. And we are looking for the stability interval of this system. And also, in the next question, we look for the amount of delay that can be added to the given system so that it becomes marginally stable. So basically, if you watch the video of the frequency methods, you will see what I mean by this. So I guess it is fairly straightforward. The questions are very basic, but the solutions may challenge you a little bit. You have to adapt to these new topics here. So and you will have all the videos available in 3 or 4 days, I guess. So that's the first homework assignment. This will be graded on its own, so you can see that this should be sum up to 100. And then we have another homework, which is a little bit more difficult than homework 3, to be honest. And here we have a real-world application, a quarter car model or an active suspension system here. This is the this is modeling the vehicle body, this is the vehicle tire, and then this is the ground that it's touching. So basically a wheel or the tire of the vehicle of the quarter car model, which means that this is 1/4 of the car. So this is just one tire and the quarter body here. So this is this damper and spring and mass constructs or models the tire and its dynamics, and this is modeling the this is the suspension here, and we have a controller that tries to basically increase the ride comfort or road handling. So now the system model is directly given, so you will not bother with this whole modeling process because it's a little bit difficult to acquire the model. There are certain transformations that we don't want to mess with. So, but as you can see, here is a little difference. We have 2 input matrices here, B U and B omega, but as this subscript tells us, this is the control input, and this is basically a disturbance here. But for this system, our disturbance and for the state space model is most of the time this road data here. So we're applying road, which is a disturbance, and we apply the control input, which is basically our actuator, and we have the system dynamics here. And we are looking for the second state in the state space representation here. You are given the state space representation, so basically our system model looks like this. You might recognize the A, B, U, C, and D parts here, but if you have disturbance in a system and if you're using the state space representation, you can immediately see that we have another input, which is namely the disturbance, and it is basically the same as U. The only difference here is that we cannot change omega. This is an exogenous input. We are not available to manipulate this as the controller, as the point of from the point of view. But we are able to manipulate U. So we have to choose U equals kx, which I'm going to tell in a minute, so that we will minimize the omega effect on the states or the omega effect on the output here. So now here are the states and all the signals that are available here in this equation set. We have ZS minus ZUS, which is ZS minus ZUS. This is directly applied to this spring here. So this is delta x times k, the force here. So delta x is basically the difference of these. So that's why that is there. And then we have zs dot, which is basically for the damper element, which is, by the way, the vertical body velocity. Since this is zs, if you take the derivative, it will be the velocity of that. Zus minus zr gives us the delta x for kus, so that's the reason why we have a difference here. And this is the third state. Zus dot is the vehicle tire velocity, vertical tire velocity. Ft is our actuator, and Zr dot is used in this model here. So omega is equal to Zr dot, but our road is Zr, so you have to pay attention to that. This is basically due to the fact that we use this modeling step. We skipped that. So if we had all the documentation here, we would have seen why this is Zr dot, but this is how it is modeled using the state space. And then we have some parameters for ms, mus, ks, kus, bs, and bus. You can see them here. They have certain values, and their meanings are given. Basically, this is like this, but a little bit more used such in a way that this is more a real world, more likely to be a real world application. It has more meaning to it, basically. And this first page gives you all the unknowns, and then this page will tell you what you should do question by question. Now, the first step here is to calculate the transfer function gu, which is defined as zs divided by u. So you have to use a, b, u, b omega, c, du, d omega, so that you will get zs u relation here. So you will take the road S0. So this is the superposition here, because we have multiple inputs, but we're looking for one input at a time, so the other inputs will be assumed 0. And the same for omega. So if you basically can handle this question, you will be able to handle this one. They are basically the same. And then the third question is to combine these so that you will get basically Zs, which is the movement of the top plate, which is basically the movement of the body. So this suspension here, this active suspension system here, models the dynamics of the quarter car. So basically what you have to assume is that you're sitting in the car and you're driving this car, and since you are sitting on a car, this car seat is attached to the body of the vehicle, and this body has a suspension element, an active suspension. Basically these three elements should be there between the vehicle body and the tire. And this tire, since this has some elasticity to it, it is modeled with with mus, kus, and bus. This is basically the tire. This whole thing is the tire, and it touches the ground. So if there's a certain road disturbance here, if there's a difference here, this difference will affect this tire, and depending on the tire model, it will affect you via the active suspension here. So basically, if you have a passive suspension here, no FC is there, you will see the outputs and you will see the effects there, but you will have too much oscillations and you will experience all the oscillations that is caused by this road. Our control aim here is to reduce these effects. So there are certain strategies and we will see them. So the first question is to model GU using the corresponding parameters here, taking ZR0. If you use the state space equation set here, you will see that this is not that big of a challenge. G omega, basically the same, just U is 0 here and ZR is not. And pay attention to these definitions. It is very important to get these here. And then you are asked to give the expression of ZS. Basically, you will combine them together. You will use this and this, and then the corresponding inputs and their sum will give you a ZS. That's not the issue here, but you are asked to generate this road surface here. This is one, by the way, as you can imagine. This is basically based on simulations in Simulink, so you can see that this time here is 1. I should have maybe wrote it down, but this is from 1 to 9, so basically 8 seconds of signal is applied, and then you should apply this and plot the open loop response. Basically what I mean by that is you will apply this to the system and you will look for ZS. Since this is open loop, this should tell you about the controller part. If it's open loop, basically you don't have any controller part, so that's that. Now the first 3 questions are basically more for analysis, and then we are switching to synthesis here. We are asked to design a state feedback controller, choose the poles yourself. So here some guessing is involved. So you should choose them by trial and error. But as a suggestion, just take them any value and then try to write a code or try to design your designing process. Once you're done, once you can see a closed loop, then try to guess the poles, try to improve them, try to improve the closed loop here. So it should at least be better than the open loop. That's what I aim here. The better it is, the better the answer is, obviously. So the state feedback controller design is in a video of mine, so you can check that out here. And then we will use a different method. So this is controller 1, let's say. So this is controller 2, where we have the controller which is a p-type controller, but the only difference here is that we will not use ZS directly. Our output is ZS, but we don't use ZS directly. We will use its derivative as a feedback. So basically we can call this a D-type controller, but you can change it so that it is a p-type controller. If you use p times ZS dot, you can change that with a little bit of thought to it. So you can adapt it so that you will have still a p-type controller design. But keep in mind that the output is different than the feedback, so you have to compensate in your structure for this. It's very easy, but you have to be careful. So plot the root locus plots during the design and plot the response of ZR. So basically, you have designed a state feedback controller for certain poles, and you ended up with a closed loop. And then you go ahead and use this D-type controller or the derivative feedback for the P, but you're still looking for ZS, and you are trying to get a closed loop here, which is, again, better than the open loop. And the last question here is to design an observer, a Limburger observer. That's again with this in the same video with feedback controller, and it is basically the same design process. If someone can design if anyone can design a state feedback controller, then it is also very easy to design the Limburger observer. You can use the dual formula, or you can just use directly the formula that is derived for the Limburger observer. So you have to pay attention to the video basically, or to your notes. It's not only in the video. You can find it in any textbook or in your notes too. So for the given system, you are asked to design an observer. Again, you are asked to choose the poles yourself. But here we have a little bit action going on. We have to assume the output so that the output has some noise in it, and this noise will affect the measurements, because we are measuring the output and the observer is trying to estimate the states. So we have to basically apply some noise to it, because that's more realistic here. And once you've basically applied the noise, you will see the effects on the response of the observer. And you can calculate NT by this transfer function here, S divided by S plus 100. So this is basically a filtering part. This is a pre-filter, and ST is white noise with variance 0.001. So here are basically two options for you. You might go ahead and use Simulink. If you're using Simulink, then you can just use this data directly and this filter here. If you're coding, by the way, you can also use this. You can have W noise, and I've given you this white noise code here. Basically, you're then generating the noise that is necessary for the system. So you can look for this code. And in both these homeworks, you will be preparing a report as for the previous ones, and the quality of the report plays a role in your in our grading policy. Now, here are some notes for you, and you are asked to upload it in our Google Classroom. Basically, what both of these homeworks try to do is try to teach you the latest part of the lecture that we've covered in the videos. The Putty approximation, the Smith predictor, a little modeling here, and then we are looking for frequency methods. This one is almost all about the state space. Keep in mind that the state space part is not that hard. It might seem hard, but it is not really. You have to get used to it. So this is why homework 4 is very important if you want to learn the state space methods. I have tried to explain the questions as well as I could. And once you've done these designs, you will see that there is a certain effect to them. You can see that one of these controllers, practically both of them, but one of these controllers will improve that. So, sorry, once you've designed this, you will see that it's very practical, and it should be fun, I think. I hope that you will think the same. So an advice could be that you might go ahead and not bother with the code in terms of simulations. You might go ahead and use Simulink as much as you wish. The only thing that I'm going to ask from you is to use a plotting style like shown here. So please get rid of those black backgrounds and some weird colors. Convert them into white backgrounds. If you do this for one scope, you can copy paste that scope in Simulink and it will preserve the styling. So please adjust the line width and the background color and foreground colors so that it is understandable and it doesn't is easy on the eyes, basically. So that's one thing. You have to prepare 2 reports, homework 3 and homework 4, as before, and you will give the necessary design steps, not the unnecessary part. You can include your code, but as I've told you before, please do not provide me just code. This will affect your grades negatively, because only code doesn't work for me. I don't need the code part because I can code it myself. What I need is that you can try to explain it using a formal report, and this is also an important part that you should learn as a skill, because that will be used most of the time in the academy, in your work in the future. So basically, it's important to prepare a report. So we have 2 homeworks. You will prepare 2 reports. You have templates in Google Classroom. And the last thing that I'm asking you is that I will upload also a template in PowerPoint, since we will not have any sessions where we will ask you any questions, or since this is not a group project anymore. I want you to fill this template here. It has some homework 3 part. You will for the first question, for example, you will put in the transfer function here, and place the Simulink block diagram that you've designed. If you have written some code, you might go ahead and illustrate that to me too, but most probably you will use Simulink since this is Smith predictor. For the second one, the closed loop response, second question, then place the Simulink block diagram. Again, some responses here. So please go ahead and fill these. So this will also be basically used for grading. You will just put in your answers here. So very basic. If you have prepared a report, you can go ahead and just copy and paste some stuff here. It will take 5 minutes for each homework probably. These are the questions that I'm asking you. So if you don't want to lose any grades at any point because you have forgotten something or you missed some sentence or a requirement, this will help you out, because if you fill this, then you have at least responded to all the questions. But if it's a good design, or if it's a valid method or not, that will be the concern that's concern of later, basically. So you have to fill this basically and upload this PowerPoint. If you do not upload this, then you might lose some grades, because this is what I will look quickly, and the other report will then grade it afterwards. So basically my first source of your answers will be this PowerPoint here. If you do not provide anything, and if that is not that much of the classroom, then I will have a policy for that. But well, so basically you will create 2 reports, and you will be asked to fill this template here, and these are the questions, and I have talked about all the aspects that is necessary. But if you still have some questions, go ahead and use Google Classroom and just post it under this Google Classroom post. If it's an individual or a private question, then you can just privately ask me. So that's it basically. I will upload some videos that will be relating to these topics here as soon as possible. But other than that, see you later then, and hope you will enjoy these homeworks, because I have enjoyed to put them together. Okay, see you all then.